welcome everybody to this day 2 of 2020. And first I would like to thank everybody for yesterday, and we are looking forward to another very interesting day here today. So the procedures will be very similar to yesterday. So I will just go through here so we come to this day. We still have the Menti up there in the top right corner, so please go in there and answer the questions there. And we will have 2 short breaks, one after the morning's 2 first speakers, and then one more later today. And we have already received questions about where we can find the presentations and so on. And they will be available, but not today. So we are working on it. So we will, well, let you know somehow when they are available. Okay, so I think I would like to start right away with the first speaker here, and that is Nils Rosmuller. He is going to talk about public safety related to fast charging zero emission buses in public space. And before I hand over to him, I will say that the procedure is the same as yesterday. Please use the Q&A to ask questions. So Nils, please, the remote is yours and also the floor.
Oh, that's great. So final check, are my slides visible, and also can you hear me? Probably you can.
Yes, we hear you, thank you.
Oh, great, yeah, just another check. Yeah, thank you very much for the opportunity to present our work that we did in the early month of 2020, in the period that we were not attacked by the coronavirus. And our research was related to the public safety of bus passengers and trespassers in case of fast charging infrastructure and buses in the public domain in the Netherlands. And I talk about we, and I did this research together with Sander Lepela. He's a safety specialist from the safety region, The Hague, and with Eric van der Staak. He's a business consultant also dealing with public transportation. And for this morning, let's see, can I go to the next slide? Where is it? Page down, probably. Yes. I have prepared some headlines for these 15 to 20 minutes. First of all, I will give you a brief clue about how the zero emission public transportation in the Netherlands is arranged. Then I briefly touch upon the system of opportunity charging, the safety risks that come into with this type of charging. And then the main content of my presentation deals with the consequences for incident management, and I will conclude with some conclusions and recommendations. But first of all, the zero emission public transport in the Netherlands. Probably many more countries as the Netherlands have to reduce their carbon dioxide emission. And in the Netherlands, we have to reduce it by 49% in the year of 2050. And some of the opportunities to reduce the carbon dioxide emission is to make adjustments in our transportation domain using renewable fuels. And we also do that in our public transportation, and not only the trains, the ferries, but also in the bus transportation. And one of the opportunities is to operate buses using electricity. So we more and more are transforming from fossil fueled bus transportation in the Netherlands to electric buses, and even in several regions, hydrogen fueled bus transportation. And in the Netherlands, we see that I put this picture at the right side of my slide. The Netherlands is a small country, but still we are very well equipped to scatter our country in more than 30 so-called regional transportation authorities, and they organize the public transportation. And for this research, the Regional Transport Authority of Overijssel, which is a province in the Netherlands, had some safety questions regarding opportunity charging and public safety. So what we did is, what does this type of charging, this opportunity charging, is all about? First of all, we checked in the Netherlands where it already was applied, which was very seldom seen. We only saw an opportunity charging system in the southern part of our country, so it's fairly new in the Netherlands. And it's a fast charging way of getting electricity in the bus for transportation. And it goes along with 400 volts direct current and 800 volts of alternating currents. And this opportunity charging is organized that the bus can be charged at several places in the public domain. For example, at bus stops where there is the charging infrastructure available. So it's not only the buses being charged at their own bus depots, but also, for example, en route during their timetables that they transport passengers. The capacity of the buses is about 400 kilowatts, and you have two different types of charging. First is the pantograph up. You have the pantograph on the bus, which goes up to the infrastructure and make contact to the charger, and then the bus is being charged after several safety protocols have been managed. The other way around is that from the charging infrastructure, the pantograph is let down to the bus, and then the same connection is established. And the most of the charging infrastructure in this case is dealing with the pantograph up system, so from the bus to the charging infrastructure. This picture gives the whole system of the charging infrastructure, but most important here is the ellipse on the right side of the picture, which is the demarcation of our research. We only looked at the safety aspects of the buses operating in the public domain where they are being charged using this pantograph up system. And the province of Overijssel, the regional safety authority, was interested in what are the safety risks for the bus passengers and third parties due to this opportunity of high voltage power charging in the public domain, because we are already aware of several safety risks in the private domain, but what is typically the additional risk in the public domain? And what we did was we studied literature, and we held interviews with safety specialists of regional transportation authorities about charging infrastructure companies, and interviews with bus companies and their safety, health, and environmental experts. And what we saw is there are three typical risks involved with this high power charging in the public domain, which is the fire that can occur, electric arcs, and the risk of electrocution. And I put a picture at the right side of the slide where we see a bus. It's in the city of Volendam in the Netherlands. It's almost 2 years ago where an electric bus caught fire. First of all, I have to say that the fire was not caused by the electricity, but by the ecosystem of the bus. But there were quite a lot of difficulties because the pantograph in this picture is still connected to the charging infrastructure, which puzzled the the firemen and firewomen how to deal with this electrocution risk. And these kind of risks are typically for electric buses in the public domain. And when you introduce new kind of technology where firefighters have to deal with, and in some cases are not aware of those risks. So what we did is we searched for regulations, and we saw a whole lot of regulations, and I'm not gonna elaborate on all these guidelines, but our conclusion from this inventarization of all kind of risks is for all those isolated parts of the electricity system, there are well described regulations, but the communication between the charging infrastructure and the bus is hardly prescribed how to communicate whether or not it is safe to load or to charge or not to charge. It is the bus company and the charge infrastructure operator who have their own degrees of freedom how to specify the communication between the charging infrastructure and the bus. So this is as we think let's say a vulnerability in the safety system of this concept. And what we saw is that in case of an incident, the bus operator and the firefighting are the key players in case of how to handle the accident consequences. And this is exactly what we saw last weekend in the Netherlands, where 4 electric buses burned down in the city of Haarlem. Again, it's not sure at this moment whether or not the fire was induced by the electricity system in the bus. It's still under investigation by the police. But what we saw in this incident is that 4 electric buses were fully burned, and that the other buses in this bus depot were safeguarded by a bus driver of the bus operating company who was able to move the buses away from the fire. This is what he did on his, let's say, on his own expertise and opportunities. But what we saw in our research is that there are no specific guidelines for bus operators and firefighters how to deal with these kind of electric bus fires. And there were also no guidelines for passenger safety related to this activity of fast charging in the public domain. So what we did is we developed some guidelines for both the bus operator and the firefighter. I will only briefly touch upon those elements that we identified. First of all, the bus operator has to be able to push an emergency button to shut down the charging process. Evacuation protocol for bus passengers should be developed so they are able to deal in a safe to handle in a safe way in case of fires. There should be a communication protocol with the safety expert of the bus operator company at the headquarters. Procedures for how to deal with those protocols, because we are dealing in the public domain with these risks. We think there is a responsibility of the bus operating company also to notify neighbors, for example, train stations or retail near the opportunity charging infrastructure. And a very important one is to develop a procedure for how to deal with the pantograph in case it's on the bus. It's important for firefighters to know and to see and to recognize whether the charging activity is being stopped and electrocution risks are minimalized. And finally, there's also relevant to take care of the incident after the firefighters did their job and to make appointments with a towing company how to deal with the bus. These are elements for the bus operator. And for the incident management, in particular important for the fire brigade is to know how to handle with the charging activity and the pantograph. And in case there is no contact between the pantograph and the charging infrastructure, you can consider a bus fire as an ordinary bus fire without the electricity component, which means that the firefighters are able to use a lot of water using low pressure and extinguish the fire like an ordinary bus fire. The difficulties originate when the pantograph is still in contact with the loading infrastructure, which means that electricity is being transported from the wall to the bus, which means that there might be this electrocution risk. And then we say, don't use a lot of water, but make a sort of precise attack to the bus in order to extinguish the fire. And in both cases, when there is contact between the pantograph and the charging infrastructure or not, get in touch with the bus operating safety expert who is able to give you the insights of the electric charging system and the risk and how to switch off the electricity from the charging infrastructure. And of course, it's important because in case of these kind of electric fires, there are also kind of toxic fire products. So you have to, after the incident, you have to deal with your own clothes and make sure they are decontaminated and disinfected, so there are no later on negative consequences of being exposed to those toxic elements. Conclusions from our research. Of course, it's really important to deal with safety in the public domain and the passenger safety. And the bus, there's already a lot of safety being, let's say, designed into the bus and also in the charging system itself, but it's in particular the communication between the bus and the charging infrastructure, which is fairly free, how to arrange this communication between the bus and the charging infrastructure. And we think it's recommended to be more precise in specifying the communication protocols for the safety feature in the system. For now, we in the Netherlands, we have less experience, less guidelines for opportunity charging in the public domain. Bus operators do not have the obligation to conduct in-depth risk analysis. So what we see is that regional transport authorities, they ask bus operating companies to make a bid for transporting bus passengers, and there is no really in-depth request for risk analysis in those bids. And the bus operator and the firefighters, for now, they lack in-depth knowledge regarding these kind of fires, how to suppress them and how to align their own activities in fire suppression. So some of our recommendations for the bus operators: specify inherent safety requirements to the bus companies. And for the regional transport authorities, elaborate the risks involving both the bus operator as well as the fire brigades. And also for the regional transportation authorities, make sure that the emergency procedures of the fire brigades are developed as well as those of the bus operators are developed and aligned with each other, so they know from each other's procedures and they know how to make use of each other. And finally, which is a broader recommendation, is that we think to stimulate safety in the public transportation, the safety aspect in those bids should be eliminated from the competition between bus operator companies who want to fulfill these bus operating activities. So it's even more easy to exchange knowledge from one bus operating company to the other bus operating company in case of safety aspects. And we think sharing the safety knowledge is key in case of these new kind of innovation in our public transportation domain. And when you have safety in the bid procedure, then this exchange of knowledge is reduced, and that's, we think, a pity and should be avoided by leaving safety out of the bid procedure of the regional transportation authorities. And that was my final recommendation. And for those who are able to read Dutch or who are able to use Google Translate, our report is available at our site, and you can download it and make use of it. And that concludes my final presentation.
Thank you very much, Niels. And this was really a very managed to include very recent accidents as well. So this is really a topic that is very interesting. So we have received some questions here, and the first one is: are there no emergency shutdown buttons on the charging infrastructure that would reduce the risk for electrocution a lot?
Yes, is this a question or a recommendation?
Yeah.
Because I fully support this suggestion.
Yeah, I guess it's both. The question is: are there no emergency shutdown buttons?
Regarding this public infrastructure, on the charging infrastructure, they are not there. So this is really a let's say a dilemma for the regional transportation authority. Putting them on the infrastructure might be also a reason for, let's say, sort of hooligans to press this button and to shut down the electricity. But then the other way around, it is also a sort of a safety element in your system. So they are still dealing with this emergency button, whether or not to position it on the charging infrastructure, and in case it is positioned at the charging infrastructure, who is able on which manner how to operate this button.
And then we have another one here. How many issues are you aware of for electric buses ending in battery issues? And that is from a runaway during the charging process.
If I understand the question well, do we have, let's say, statistic or numbers about the number of fires in electric buses?
Yeah.
Is that what
and how many of these do proceed to also involve a battery?
That's a great question. We did some research in 2000, and I think it was 2016 or 2016, I think it was, about the numbers of electric bus fires. We couldn't find any empirical data or data sets which gave a clue about the number of fires, for example, also expressed in the number of bus kilometers or bus operations. And also we could not find any kind of numbers or proof in how many cases a bus fire proceeded and which caused a thermal runaway. We do not have those figures we did not have those figures in 2016, and still we don't have them in 2020, which is a pity, and we should make, let's say, work of it in cooperation with, I think, the bus operating companies.
Finding data is always an issue. We have one more here. What are your opinion about electrical buses? What's the biggest problem for the fire brigade?
I think the biggest problem is that they know now, today, they are, let's say, faced with those kind of infrastructure without being involved in the process of thinking how to deal with those infrastructure, where to position those opportunity charging infrastructure. And once the buses are in operation, they might be, let's say, surprised that there is already this kind of infrastructure in their area, and they have to deal with the consequences in case of accidents. They are caught by surprise, which is not, which which should be prevented in order to, let's say, establish the contact between the regional authority bus operation company and the firefighters. And then they are able to understand the safety risk of the system in the public domain. And then they are also able to develop standard operating procedures for themselves as well as for the bus company.
Okay. So, and then we have one more, I believe, final question perhaps. So have you received any feedback on your report yet? I mean, it's out now for the bus companies and the rescue services. So have you received any comments? Do we think it's good, and what new developments are needed in order to really be able to use it?
We got some feedback, of course, from the regional transportation authority, who was really happy with the results. First of all, the result that electric buses are not more risky than traditional buses, which is also a conclusion based on a qualitative way of research. But what they really were happy about is that they were now able to specify more detailed the requirements for the bus operating companies, that they should make serious work of their own emergency procedures in case of public domain opportunity charging. So this is where they are making the next step to the bus operating companies to, let's say, force them to really make serious work dealing with safety risk in the public domain regarding to opportunity charging.
Okay. And then we take one final one, actually. So are there any conclusions or studies done on what is the best way to extinguish or control this type of fire?
This is really an interesting question. We did not perform real-life tests dealing with several kinds of fire tactics. What we did is we examined the risks, examined the safety systems of the charging infrastructure, and we examined our standard Dutch operating procedures in case of dealing with bus fires. And thinking, and then we came with this, let's say, standard operating procedure. And yeah, the question is really interesting. How could you support or make clear or validate that the way we think this is a good procedure is really the best procedure? We don't know, actually.
Okay, thank you very much. So we should get ready for the next. Okay, there it is. So sorry for the, it's quite tricky sometimes to control this. So the next speaker is from Finland. It's Vesa Linja-Aho, who will talk about hybrid and electric vehicle fires in Finland. So I will start the presentation here and give you control.
Okay, hope everyone does hear me.
Yes, we hear you. Thank you.
Great. Good morning or night or evening or day or whatever. My name is Vesa Linja-Aho and I work for the electrotechnical standardization organization SESCO in Finland. And the topic of my presentation is hybrid and electric vehicle fires in Finland in 2015 to 2019. And here is my email. Feel free to contact me after the presentation if you have any questions on it. Okay, yes. Here is a short introduction of me. I'm currently the main reason for this presentation is that I'm in charge of preparing the electrical safety standards in Finland, which includes the safety standards for electrical vehicle charging. And I'm also doing my PhD to Aalto University on electrical safety of emerging technologies, including electric vehicles and solar power systems. And my background is in automotive electronics, so I'm an electronics and electricity expert, not a rescue personnel expert. And the vehicle fires, the ignition sources, as many of you know, they are similar to ignition sources in structural fires. We have electrical arcs and heating contacts and mechanical sparks and overloaded wiring. And arson is one reason in vehicle fires. I remember yesterday in one presentation there was a statistics from UK where the arson was like about 50% of vehicle fires where the reason was arson, but in Finland it's lower. I will get back to it soon. And electrified vehicles, we have battery electric vehicles, PHEVs, so-called plug-in hybrids, and then normal non-chargeable hybrid electric vehicles. And the new risks, as in many of the presentations mentioned, they pose new risks to fire personnel. We need lots of water, and then might be when the battery burns, it will emit hydrogen fluoride, and then there is always the risk of reignition. It's not rare; it's almost a rule, not an exception. And this work explores fire incidents with electrified vehicles in Finland. Finland is an industrialized country with 5.5 million inhabitants, but the area of Finland, the total area of Finland, it's about the size of Germany. So Finland is very sparsely inhabited country, which makes some challenges, and of course there are some pros in it too. Vehicle fires are quite, the level of fires is quite normal or average in Finland. Of course, it depends in which country you compare to, but it's like passenger cars, a little over 1,000 cars per year are burned down. And we have in total 2.7 million passenger cars, and the fire rate per 10,000 vehicles, it's about 5 or 4.7, and it's about the same for vans or pickups, and for trucks it's higher, and for buses even more high. The methods in this study, I was reviewing a National Rescue Task Register called Pronto, which you can very freely search for fires and traffic accidents. And the power source of vehicle, it's not identified in the database. So I have to use extensive keyword search, like for known popular car makes or models which use electric hybrid drivetrain, and then of course words like high voltage battery or hybrid or electric and things like that. And from that I got plenty of results, and then I had to prune manually mismatches of. And then about the fires and crashes I identified, I performed content analysis to them to find out which similarities and differences the incidents had. And we have a positive problem because the 2.7 million cars total, and the electric vehicles are quite a new phenomenon in Finland. We have only, if we look at last 5 years, we have only 2 battery electric vehicle fires, and the main reason for that is that the number of cars, it's counted in thousands, not in tens of thousands. Plug-in hybrids are more popular, but still there are only 1 fire of them in these years. Hybrid electric vehicles, we have tens of thousands of them, and they are all of them are getting more popular and popular, but still the incidents are quite rare. With hybrid electric vehicles, of course, there's a possibility that not all are logged in Pronto, but or the knowledge of the fact that the car was hybrid is not necessarily written in the register. And then one hybrid bus burned, and then one straddle carrier with the lithium-ion batteries was burnt in 2016. The fire rate, it's very low, but of course, if we look at the number of the BEVs, we have one fire here. If we had 2 fires, it will double. So the total number of fires is so low that no strong conclusions can be drawn about the fire risk. Of course, we can say that the risk is not, it doesn't differ from the regular gasoline engine or diesel engine cars, because otherwise this would have been higher here, and the vehicle stock is quite new also. We cannot say what happens when they are 15 years old, those electric cars. About the fires of the hybrid, normal, non-rechargeable hybrid cars, 4 of the fires were started while driving. The car started burning from the head of the car, from the motor space. And 2 fires happened when the car was parked. One fire started from mains powered engine preheater. In Finland, we have very much those outlets on parking lots where you can preheat your car at winter when it's freezing cold. It's a common habit in Finland to warm up your car. I think this is everywhere in Scandinavia, the same thing. And one fire was started from, it was practical misuse or stupid act from the owner. The windscreen washer tank was frozen, and the driver put electrical heater in the engine compartment of the car, and then left it unsupervised. Well, what could go wrong? Well, the car might burn. In almost all the incidents, in crashes and the fires, the rescue personnel knew quite well how to de-energize the vehicle and how to extinguish the fire if there was a fire. One exception is the incident with that lithium battery straddle carrier. It caught fire, and the fire brigade thought that, well, it's a lithium battery, we cannot use water, and then they used CO2 instead. Well, it works too, but water would have been more efficient. I think if this is only in Finland, this problem, but is it in other countries too, that we have in school, we have on chemistry class, we have a usual demonstration where the teacher throws a piece of lithium metal in water, and then it will start burning because the hydrogen will lit up. And from that experiment, many people think that if there is lithium, you cannot use water. I don't know if you have the same misconception in your countries too, but in Finland, this is quite old misconception, and of course in the media and in the training for the fire brigades. Now, I think now this would not happen. I think the majority of fire brigades know how to handle lithium batteries. In one roadside accident, the rescue personnel were unsure how to de-energize the hybrid vehicle, but it didn't hinder performing the task. It was just there was no fire in this incident. And we have, in those years, I identified 19 hybrid and electric vehicle road accidents, crashes, and driving out of the road. And in none of them, the vehicles started to burn. However, one of the incidents was such that the hybrid electric vehicle was driven off the road accidentally on previous day, and then on next day it caught fire when driving. So if the car is damaged in a crash, it should be inspected, not just hope that, well, everything is okay. Same applies to all electrical appliances. Don't use them if they are broken or suffered damage. Causes of all vehicle fires in Finland, they are also recorded in the Pronto database, and this is for the all vehicle fires, including boats and all other vehicles. Technical fault is the main reason, and the second one is human action. And from human action, when the reason is human action, the most common reason is arson then. So arson rate is quite high. If in UK it's over 40%, in Finland it's 11%. We have quite old car stock in Finland, so the older cars seem to catch fire easier than new ones. If we consider arsons, EV battery is hard to ignite from outside of the battery. It usually needs that internal short circuit of a cell. Then those case examples of electric and plug-in hybrid vehicles. Hyundai Kona Electric has had that some problem in the battery cells, which have now I understood that it's fixed for the software. It should be the battery management system should now be able to detect this kind of heat rise better and limit the charging current. But this was before that, and Hyundai Kona Electric caught fire in the front of a car dealership in Lahti, which is a small city in Finland. It was plugged in, but I think the charging was finished because this was like after 5 a.m. in the morning. There is more details in the conference paper on this incident, and there is also a Finnish Firefighters Professional Magazine report on the case, so you can read it with a Google Translate. The reason was internal malfunction in battery, probably same as all the Kona Electric incidents over the world. And one thing was here that the fire brigade put off the fire, and then when couple of minutes after they left the scene, the car reignited, and then the fire brigade extinguished it again, and then it was again it reignited. So it was a tough one, and so it ignited 3 times in total. Then this was a year before, 2018. It was a Think City. It's a small plastic electric car. I think it was not very popular, at least in Finland. There are a couple of those cars in Finland. And this vehicle has a high temperature battery. It's called molten salt battery or zebra battery. And that's why it has to be plugged in every you cannot leave it without the charging cable for 1 week, for example. The car stopped working on the road, and then the tow truck transported it to the owner's home, and there it was waiting to be delivered in the repair shop. And a week after this, the car caught fire at night, or it was near the morning. I think it was like 8, not at night, but the owner was sleeping. The owner woke from a banging noise. The battery was keeping those banging noise. The cells were exploding or bursting, and because the car was near the building wall, there was a risk of fire to the building. So luckily the owner woke up and the car was extinguished. I think lesson in this story was that if there is a malfunction in the car, don't park it next to your building. Just try to get it fixed in the repair shop soon. Then this was a plug-in hybrid Volvo. Actually, here is a small mistake in my slides. It was the neighbor who called the emergency number. It was about at midnight. The owner was at home, and a neighbor noticed that there is smoke coming out of the car, and the neighbor called the emergency number, and then the owner de-energized the charger, and the firefighters, because there was smoke coming out of the location of the battery. It's in this car, it's in the middle tunnel of the car. The firefighters, they were experimental. They drilled 2 holes to the traction battery and to get water inside the battery. And in Pronto, it's always logged how much water was used in the rescue task, and they used like 4 cubic meters of water. And then the car was transported to a salvage yard, and the firefighting unit escorted the towing truck to the yard. The charger and the charging cable remained intact, so it was probably a battery fault, as these usually are. On this year, I usually like to look at full years in research, but this year is still ongoing. But due to 13th of this month, there were 4 no electric vehicle fires, or full electric vehicle fires, but 4 tasks with hybrid vehicles. 2 of them were regular non-rechargeable HEVs, which caught fire when parked, and then 2 other, they were the accident reports were a little weird. The car was there was emitting smoke when driving under the hood, but then when the fire brigade arrived, there was no fire nor signs of fire. So I think some plastic or garbage or something was dropped on the exhaust manifold, and it was emitting smoke or something like that. So no fire, just smoke. Conclusions and recommendations based on these few incidents. I think in Pronto, the accident register, the fires should be logged more efficiently. If there is a high voltage battery or lithium battery in the car, it should be there should be one cross you have to put on the report if it was this kind of car, and also the emergency response staff, the people who respond to emergency calls, the software they use, it should instruct the officer to ask if it's an electric car. This might have been fixed this autumn, but last time I was getting information on this, it was not such a case. And if the vehicle has been crashed, even mildly, or is waiting for service, it should be parked so that if it catches fire, the fire does not spread anywhere. This is usually easy in Finland, as this is a sparsely inhabited country. A safe place to charge vehicles, it's always use the parking lot. Don't park it next to your building. And it's of course same with all vehicles and heating those vehicles, but parking place, it's a good place to charge, not next to your house. This is lacking in Finland. We have had a training to firemen, and we have had courses on this for the superiors of rescue personnel, but there is still no simple rules. They should fit on one A4 to instruct how to put off these fires and how to handle crash accident involving an electric vehicle. A good example is in the United States, the SAE standard for hybrid and electric vehicle suppression. This kind of simple instruction. Open questions on the data. The hybrid electric vehicle number of fires, it's probably larger, but if the car has already burned, the fire stuff would not necessarily write it down to Pronto that it was a hybrid car, because if it was already burned, there is no reason to check it. And for the small number of fires, we can draw no strong conclusions on the fire risk, where it is and how it does. But overall, we should wait till the electric vehicle stock gets older. Then we see how they behave when they are old. And the accuracy of Pronto records, it's sometimes the recordings are very short, and there is no exact writings on what has happened. And one thing which could be examined for all vehicle fires, we have good registers, but we should combine them, check, for example, the year of the car when it was made, and compare the risk of that age and fire risk.
Sorry to
Okay,
interrupt.
now the questions.
Yeah. Yes, thank you very much. This was very interesting. I mean, it's a very thorough study, and still it's not so much so many incidents, but a lot of information still can be drawn out of it. And we have received several questions here, and first one concerns the database. And who is it that decides the cause of a fire? Is it the fire service, or is there data taken into this to the Pronto database in another way? Is it the vehicle manufacturer or another third party?
Yes, this is simple to answer. It's the fire service in Pronto, and there is one problem is that even if the fire was investigated closer by the insurance company, for example, the reason might not be updated to Pronto. So this is mainly the fire, and if it's suspected that it's a deliberate fire, then the police will investigate it. But sometimes things go to court, and then there is a fire investigators report and things like that. They are not necessarily updated to Pronto.
Okay, thank you.
So there might be discrepancies. Okay.
And so we have a question here. What are the requirements in Finland for EVs involved in accidents without having big visible damages? Are we required to be checked and or isolated, or so what is the procedure actually?
Okay, they are not. If there is no big visible damages, then there are virtually no requirements. The fire department usually recommends that take this car to a repair shop to be checked, but only in severe crashes they have to be re-inspected. And there is, by the way, one problem that the procedure of, for example, if the electric vehicle has been crashed very badly, who inspects, for example, that the battery is intact? There are currently we are preparing rules what and who and how should it be inspected.
Okay, thank you. And so we have one more question here. Very good presentation. Do you believe insurance companies should increase prices on house insurance if not separate garage is available?
Okay. Well, I think insurance companies they should maybe I think they should. I should maybe consider longer this answer, but I think if you store your electric vehicle in your house, which is attached to the garage, the insurance company should take it into account somehow. Of course, when the electric vehicles are new, the risk is quite low, but maybe insurance company might issue some new recommendations on this. I will, by the way, I can answer there is a lot of questions. I can answer them by typing here if my time is running out.
Yeah, that would be excellent. I mean, there is
Yes.
a lot of questions. So,
And please send me email if you have any further questions. I will gladly answer them.
okay, thank you very much, Vesa. So
Thank you.
now it is time for a break, and so we should be back here at 5 minutes past 10 Central European time, so in 10 minutes. So, well, welcome back then. Thank you.
För det är ju den som ligger, mötet ligger ju där. Okay, welcome back. So now I'm here again. So for you who attended yesterday, knows me. So I'm Ola Wistrand and chair of the organizing committee for the FIRE conference. So we start directly with our next presentation and next session here. So it's Renato Mole Antionasa that will speak about heat release rate recovery from indirect measures application to vehicle fires. Are you there, Renato?
Yeah. Hi.
Hi. And I will just start your presentation.
Okay.
And then you should have the control. So
okay, control it's okay. Beginning. I can.
Yeah, you're welcome.
Okay.
Go ahead.
Hi everyone. I'm Mole Antonazza Renato. I was a PhD student until November 5th, 2020, when I defend my thesis. I worked in police department labs in Paris, and now I will present a part of my thesis work about heat release rate calculation from indirect measurement applied to vehicles fire. I divided my presentation in three parts. I begin with the short context of my thesis work. I will present our methodology that we developed, and I finish with the main result about the fire vehicles. And what is the context? In the police department laboratory named Laboratoire Central de la Propriété de Police in French, in fire investigation operate in Paris and the suburbs in fire investigation to identify and determine the fire origin and the sequence of the fire. In three cases, we need to check the hypothesis, to simulate, to use a numerical simulation to check this hypothesis. This tool is also used in the Laboratoire Central to in fire safety engineer to study the fire impacts in the building or on the scale to the city to study the smoke dispersion. To work, the code that we use for the numerical simulation requires main parameters, key parameters, the heat release rate. This is the main unknown of this presentation. And this data can be evaluated experimentally by measurement of mass loss rate with weighting scale or oxygen consumption with large-scale calorimeter like vehicles in a right picture. But these measurements are limited. When you want to install the large-scale calorimeter, for example, in a car park, that can represent a significant cost, can be complex to do that, or ever impossible. And this measurement, the mass loss rate and the oxygen consumption, can be used only on well-ventilated environment. We need to evaluate the heat release rate in situation, or for example, in a car park. We need an alternative measurement. What is this alternative measurement? All experience, we use thermal couples to measure temperature, gauges to measure heat flux, or McAfee probes to measure velocity. And if we can use this measurement to evaluate the heat release rate, if we compare to the previous measurement of mass loss rate and oxygen consumption, this indirect measurement are simplified since installation is commonly used in all laboratory, and you can use in anywhere. You don't have limited by environment. From this measurement, we're taking this problematic, are we able to rebuild the heat release rate from indirect measurement? To answer this question, we developed a methodology based on use a CFD model Fire Dynamics Simulator, FDS. We've defined our problem as optimization one, and to resolve this problem, we use a machine learning method. And now I'm presenting your methodology and the programs named Obi-Wan. We have this situation of vehicles around. We measure temperature, heat flux, velocity. I plot one example in the right graph in a solid blue line, one example of measurement. And from this measurement, we try to rebuild the heat release rate of this vehicle's fire. In first approach, we can model several many heat release rate. And if we compare the final state between numerical output and experimental measurement, you can find the heat release rate that allows us to rebuild, to reproduce the measurement. But this approach used in fire investigation lacks accuracy. In your methodology, we base our methodology on time discretization. We use the fact that we have continuous data with measurement to create time marker. We divide our time in interval, and we try to reproduce in each interval the measurement. To do that, we set the heat release rate in each interval in two steps, the exploration step and the estimation step. The exploration step consists to simulate n heat release rate in each interval. We use for that FDS, and the output of each heat release rate and the value of heat release rate form a learning set that we use to in the machine learning method named gradient tree boosting. This method is based on regression and estimate the function that we denote here G, and this function links the measurement to the heat release rate. Once this function is established, we can apply it to experimental measurement to evaluate the heat release rate, allow us to reproduce this measurement. With this value, we use this value in the next step, the estimation one, to simulate, to continue the fire simulation and to reproduce the measurement. If we repeat this operation in each interval, we reproduce the measurement and rebuild the heat release rate allows to reproduce this measurement. All operations are automated in the programs that we develop and we call Obi-Wan for optimization-based iterative workflow for a numerical experiment. This programs is developed in the Python language, and we give as input data only two files, the geometry model with FDS and the experimental data that we use to reproduce to rebuild the heat release rate. Obi-Wan is executed on the police department cluster composed by 80 CPU, and we have as output data the heat release rate rebuild and the comparison between the experimental measurement and numerical output. I present now the Obi-Wan, and we want to know if does Obi-Wan works, because in fact we before his application to the experiment, it's okay. We want to know if Obi-Wan work correctly, and to do that, we submit to Obi-Wan a numerical simulation. this is a fire coach fire that we know the heat release rate. From 5 temperature calculate on right of the coach, we try to rebuild the simulate heat release rate. Now I present only the best result obtained with OB1, and from this 5 temperature, we observe in this graph in a solid black line. This is the first simulate heat release rate, and in the dashed brown line we have the output of OB1. We observe that that these data are closed and OB1 works correctly, and we defined the settings that allows us to rebuild correctly this heat release rate. We fix 3 parameters. The experimentation time is fixed at 60 seconds, estimation time at 830 seconds, and we simulate 20 heat release rate in each time interval. OB1 work correctly, we can apply to an experiment. This experiment, the experiment platform is composed by a large-scale calorimeter where we measure oxygen, dioxygen, and carbon monoxide concentration to evaluate the heat release rate experimentally that we compare to the output of OB1. We measure to give OB1 experimental data 7 heat flux measurement, and we record all experiments with video footages. The first fire of this experiment, thus this is the fire loads, composed by 5 wood pallets, 6 plastic pallets as a combustible material, and non-combustible we added bricks and steel bar. We model this fire as an inheritable block. Those physical properties are weighted average of plastic and wood, and all surfaces are burning. We try to rebuild the heat result of this fire from only 3 heat flux measurements, about 7 initially. These 3 heat flux measurements are represented in this picture by the green, the orange, and the blue parallelepipeds, and we try to rebuild now the heat result. I'm showing here the result from this reproduction of this measure. On the left graph, we have experimentally in the solid color line the experimental data, and in dotted line we have the output of OB1. We observe that these data are closed between the numerical and the experimental data. If we observe now the heat release rate on the right graph, we have in the solid black line the evaluation of heat release rate by oxygen consumption, and in dashed brown line we have the output of OB1. We observe in the grow and the stationary phase these 2 data are closed, but in decline phase we have the differences. These differences can be explained by our previous assumption about an unilateral block. We consider the fire as an unilateral block, and this hypothesis can permit to take account about that plastic melting and the coal formation. The second fire, this is a vehicle fire. We take a passenger car and converted it to a light commercial by obstruct the rear windows by plywood panels. The tank was filled and the trunk was loaded with previous material. We can see in the picture the woods and the plastic pallet. And we, at the first approach, we do the same assumption like a fire loads. We model this car like an unilateral block. Those physical properties are weighting average those plastic, woods, and foam. We have only one burning surface on the top of the block, and we try to rebuild the result of this vehicle's fire with 3 heat free measurement, like previously. These 3 measurements are represented in the picture by green, blue, and rose parallelepipeds. And now I will showing you the result for this simple design. On the left graph, we have the same things. The experimental data is on solid color line, and the dotted it is the numerical output of OB1. We observe on the left graph that orange heat flux is close to the numerical and the experimental data, and between the blue, for the blue and the green heat flux, we have the differences between the numerical and the experimental data. If we focus on the right graph, the heat rate, experimental heat rate in solid black line is overestimated by the value obtained with OB1 in dashed brown line. And these differences can be explained by the not well reproduce of the heat flux If we focus now on the left graph, particularly for the blue and the green heat flux, we see experimentally in solid color line between the blue and the green, we have differences, different asymmetrical measurement between these two heat flux. That means we have different phenomena between the front of the vehicle and the rear vehicle. Now we study the video footages to defining this phenomena and to update the fire source to increase our result. This is the video of this fire. We observed the fire has been starting and spreading to the front initially, and secondly to the rear. We observed that by a plywood ignition. At the rear now, we have the rear windows has been burning. That explain the increase of the green heat flux experimentally. We take in account of this ignition of the plywood. We take in account in a more realistic design of the car body, of the lateral front windows and the lateral windows obstructed by plywood panel, and we model 2 burning surfaces, one on the top of the front of the vehicle and one inside the vehicle, to take in account of two spread direction. One to the front and one to the rear. From 3 heat flow measurements represented here by the green and the blue parallelepipeds, and 1 orange parallelepiped hidden by the car body, we try to rebuild the heat rate. The heat rate of these fire vehicles with more realistic design on the right, represented on the right graph. We have in the black solid line, the evaluation by oxygen consumption is close to the output data obtained by OB1 in a dashed brown line. But if we take this result and if we compare to the heat flow result, we observe for the blue heat flux, we have an overestimation by OB1 of the heat flux. We have a good, well reproduced of orange and the green heat flux. And this is the first step. We succeed in rebuilding the heat result, but only by a compensation effect between the well reproduced heat flux and the blue one overestimation. This is the first step, and we must to improve our method. And to do that, and to conclude of my presentation, I will summarize the result. We well reproduce the influx and we rebuild the HRR for loads of fire, but this is a simple fire without complex phenomena. And we have for the vehicles fire, we well reproduce the heat release rate, but we not well reproduce the heat flow measurement, because the heat flow are very sensitive to the shape to the flame, and the accuracy of our numerical simulation did not permit to do increase this sensitivity, to taking account of this sensitivity. And we observe a complex fire spread between the front and the rear of vehicle, and we didn't model numerically this complex fire spread. That explains our result. To apply our methodology OB1 to a more complex problem, we need to OB1 recur improvement. We want to program multi-periodic surface with different heat release rate, coupling heat flux and temperature for the same problem, because actually we use only heat flux or temperature, and we need to modeling more complex phenomena like under ventilated condition or complex fire spread like a vehicle's fire, like a previous vehicle fire. From this improvement and from this result obtained with OB1 for the pool fire and confined environment, we have this heat release rate evaluated by max loss rate kilometers. We reproduce this heat release rate from 5 temperature measure at 1.5 meters of the center of the fire at 5 eggs, different eggs. We observe in the right graph, we have a well reproduce of the temperature, and on the right and the left graph, we well rebuild the heat release rate, the numeric experimental heat release rate. From the previous improvement and from this result, we can imagine in the future apply our method to evaluate the heat release rate of the fire vehicles in a car park where the large scale kilometer cannot be used. Thank you very much. I will be pleasure to answer your question.
Yeah, thank you very much, Renato. Very interesting presentation. So we have one question here. So which type of heat flux meters did you use? And do you think the results are sensitive for this?
Can you repeat the question?
What type of heat flux meters did you use for measurement of flux?
Relative heat flux.
And do you think it's sensitive to what type of heat flux meters you use? I mean, different heat flux meters could measure both radiative but also convective heat.
We use a relative heat flux, and we have a post-treatment of the data in the OB1 to take into account of incident heat flux, just only the incident heat flux.
Okay, so do we have any more questions? Yeah, okay, so how many meters or heat flux meters are needed to accurately reproduce the heat release rate, do you think? Did you hear the question?
Yeah, okay.
How many heat flux meters do you need to accurately reproduce the heat release rate?
Actually, we need we use 3 heat flux meters, but we can use 4. And if you for the simple fire like a loads fire, we can just use 1 or 2 heat flux meters. But this one or two effects meters, we are must to do have a good place around the fire.
Okay, thank you. So one last question here is then from the Q&A. Magnificent work. Is there any other experiment data you or your colleagues tried OB1 on already? For instance, house fires.
Well, my previous year, I use OB1 in the confined environment. We used to rebuild the heat rate of the fire pool or gas burning with only 5 temperature.
Okay, thank you. So now we move on for the next presentation. Thank you very much.
Thank you.
There we are. Our next two speakers is Gumaler and Paola Russo, which will talk about recent safety-focused overall analysis, testing, and accident reviews towards safer e-mobility and energy storage.
Yes, thank you. Can you hear me?
Yeah, we can hear you, Paola. And
okay.
yeah, so I will just start your presentation.
Can you also hear me?
We also hear you.
Okay.
So the control and word is yours, Paola.
Yeah. Okay. So, okay, it works. Okay, so good morning, everybody. Thank you all for your presentation. My name is Paola Russo. I am Associate Professor at Sapienza University of Rome. And I'm going to present you this joint work between France and Italy about recent safety-focused overall analysis, testing, and accident review towards safer e-mobility and energy. So firstly, I'll give you an overview of the experiments carried out in Italy in collaboration with the colleagues of ENEA and the National Fire Corps on lithium-ion cells and batteries. And then I'll move on the accident database implemented by collecting accident information from different sources. Then I'll give the floor to Guy, which will describe the activities carried out by NERIS. So also in this case, he will show you the incident-accident review. He will focus on two studies, and also he will show the activities implemented, the standardization activities implemented in the last 3 years at the level of IEC TC 120, and then he will show you the experimental test performed on multi-scale level at NERIS during the project demo base. So first of all, regarding to testing carried out in Italy, we have analyzed the behavior of cells and batteries under electrical and thermal abuse condition. As you know, lithium-ion cell can operate efficiently in a certain range of voltage and temperature. And when these conditions are not fulfilled, a lithium-ion battery or lithium-ion cell experiences an abnormal condition that can occur during charging or discharging or also no working process. This can lead to thermal runaway, which can further result in a fire or an explosion. In particular, I'll show you the results of tests performed on NCR 18650 Panasonic cell, charged at different state of charge from 0 to 100%. The tests were carried out in a ISO 16550 cone calorimeter for HRR measurements, and in this test the external temperature and was monitored, the VOC concentration also was monitored, and we recorded by video camera. What I want to show you here is are two tests at the same state of charge of cell, full charge, and irradiance of 50 kilowatt per square meter, and on the bottom 35 kilowatt per square meter. As you can see, during the test, three main phases were identified: venting of gases with the ignition of this, and then the sail failure and the launch of fragment. So what we can observe is that decreasing the irradiance, flame and explosion occur at a longer time. We also investigated the effect of state of charge, and as you can see, what happened is that when you decrease the state of charge of the cell to 50%, it determines an increasing in time at which venting, flames, and then explosion occurs. So then these are the results in terms of that I previously showed in terms of heat release rate and temperature as a function of time for a cell at different state of charge. The red curve is the one with 50% of state of charge, blue one to 100% state of charge, and the black one at 0% of state of charge, or we can say an over-discharged cell. So you can see that the state of charge influences the onset of thermal runaway, and an unexpected result was found in the case of a discharged cell, because in this case the thermal runaway occurred at shorter time, and the cell fails earlier than the other cell. So we have analyzed the literature, and we have found that in the over-discharge condition, the primary risk is presented by copper dissolution at the anode and deposition at the cathode, so it can cause the growth of dendrite and eventually resulting in a short circuit. Some other researcher reports that also over-discharge as an effect to dissolve the CI layer between 0 and also up to 10% of state of charge. So these results are justified by the literature results. Then we also perform other type of tests, especially because we are working with the National Fire Corps. They were interested in how to extinguish the fire in the case of this type of cell, in the case of electric vehicle. So we tested this punch cell at 50% of state of charge. The cell was exposed at the flame of a LPG burner, and the temperature of the cell was monitored by thermal imaging camera, and also video was recorded. And during the tests, we firstly heated up the cell up to 600 degrees C, and then when the cell reached this temperature, we applied the extinguishing agent. In particular, we applied three different agents like carbon dioxide, foam, dry powder, pure water, and water mist. And you can observe that we obtained a very fast extinguishing effect in the case of foam and the case of water, while less effective looks water mist because of difficulty to disperse the water with all the cells, and also the other two extinguisher, CO2 and dry power, are less effective. Okay, so these are the results of our experiments, but we also carried out, as a part of a working group nominated by the Italian Minister of Interior and composed by people from INEA, from National Fire Corps, from university, and also an association that works on battery, COBAT. And we, in this working group, we focused on the assessment of the risk associated with the storage of innovative storage system. In particular, we worked on the preparation of specific prevention, protection, management measures to reduce fire and explosion risk during their storage. The work consists of 7 chapters, about 600 pages. Is in Italian, unfortunately, but you can download at this link. And we also carried out an accidentology analysis, and we realized an accident database, and the analysis includes different lithium-ion battery application, from electric vehicles, energy storage system, consumer devices, and so on. So what we learned from this accident, this is a short video.
To investigate a video that appears to show the explosion of one of its cars parked in a garage in China. The video was posted on Twitter, but has not been independently verified by CNBC. As you can see, it started with smoking and then an explosion. Shows that smoke coming from the hood of a Tesla that's parked in the garage, and then the car bursting into flames. Again, CNBC has not independently verified this. Tesla is apparently sending a team to investigate and help authorities there.
So the first information that the first awareness of the incident involving battery most of the time come from the media. Among those reported incidents, those incidents leading to publication of useful investigation reports are very scarce. While we consider that collecting incident and accident relating to lithium-ion battery in a consistent way is of key importance. And in particular, it's important for manufacturer, for end user, but also for first responder. You can see in this type of accident, in this case, the first responder collected the battery of the car by hand. That is very dangerous. And so first responder has to know what are the risks in their activity. And also we have found that incident may occur for different vehicles when the vehicles are in different places, in open or in confined spaces. Of course, if you have a confined space, you can have a very huge fire like the one in the Moto E paddock that destroyed a lot of electric bikes, 18 bikes, and because of this, there were no injuries, but the first event at Jerez has been cancelled last year. So it is important also to know that this type of accident occurs also in different situations when the vehicles are parked or during driving or during charging. This is the case of a huge fire at electric bus charging station in Beijing. And because of this fire and several high-profile vehicle fires occurred in China, and also because of increasing number of fires that in China that killed in 4 years about 158 people. So what happened is that China issued last May 3 mandatory standards for the safety of electric vehicles and their battery. And these new standards are set to be enforced in January 2021. and they will be related to emphasize to the system safety of the batteries, but also the electric vehicles, in particular electrical bus. So this is my part of the presentation. I think I have to leave the floor to Guy. So
yes, Paula, may I request the floor by now? Paula?
Yes.
Okay. I'm not sure I can control. Hola, may I get the floor?
I can give it to you.
Okay, thank you much.
So now you should be able.
I cannot display my, okay, I'll try to. Let's see if it works. Doesn't seem so.
If you click once, now I think.
Yeah, oh, okay. So Guy Marler speaking for the second part of this presentation, and I will start by continuing a little bit on incident lessons that we can have from recent past accidents involving batteries, in particular to outline that we have some early signs that we might also fear some system level safety issues, and this will be illustrated by two incidents a little later in my slide. What I would like also is that these system level incidents lead to enlarged standardization activity, in particular within the IEC TC 120, which I'm chairing currently, where we are looking at electric energy storage system, system safety. You have two examples of standards there. The first one is dealing with safety requirements in grid integrated EBS systems. This is already published and already going into an update work. And the second document is really motivated by the Korean incidents that took place quite recently, on which I will come back as well. And there's a new standards being implemented as a consequence of this. So first of all, I would like to mention a little bit what we learned from the car ferry Itero-Honningen incident that took place in Norway in October 2019. It was a conventional ferry that was converted a few months ago before the incident into a hybrid car ferry. There was an electric powertrain added with a 2 megawatt-hour EES system based on lithium-ion batteries. There was a dual fire protection of the battery room by a gas inerting system, Novec 330, and also a water sprinkler system. There was initial component failure dealing with a water glycol cooling system leak that led to starting fire, which was at some later time detected, which led in turn to activation of both suppression systems in the battery room. But the system failure that were identified from the ongoing investigation was that there were no special control or check after some service provided on the battery thermal management system of the battery pack. There were no early reporting of the incident by the BMS to the main control room, just because the ferry was cruising on the diesel engine at that time. And there was also chiefly inadequate use of salt water in the sprinkler system that eventually led to triggering short circuits. At the time, we have not the complete final investigation report, so I suggest you to follow this at later stage. You will have some information from that web link as well already. So the most important one I wanted to mention in terms of incident learning was about these fires that took place in a variety of electric energy storage systems in South Korea, which were connected to the government promotion of the use of renewable energies, or it was connected mostly to photovoltaic panels or windmills. And as you may see from these figures, with so large energy storage system, it may go to very impressive fire events. And what we learned from the first information is that there were no single component reason for these fires. It was most because it was system level failures like inappropriate layout, inappropriate building, housing, or inappropriate overall management of protection of short circuiting, external short circuiting, and also inappropriate consideration of the environment in which these ES systems have been implemented. But my main topic today will be about the DIMA-based project, which stands for design and modeling of improved battery systems and efficiency. In other terms, it was promoting integration of fast innovation in electric vehicles, fast innovation regarding the progress that are currently made in lithium-ion batteries and lithium-ion cells. So one key aspect was developing a multi-layer barrier against thermal runaway propagation from cell to nearby cells and from clusters to other clusters and from modules to other modules. And this is on the left-hand side, you can see the testing chamber on which we put the test samples. So the test samples, you have a look on the right-hand side. Here we are looking at a so-called cluster containing 3 pouch cells. These cells are NMC 111 graphite cells of 19 ampere hour of capacity. They're grouped in parallel by 3 to form a cluster. That cluster is containing, is protected by a heat barrier, and within the cells we have heat sinks. And of course, there was a full instrumentation rendering us capable of measuring all the gases emitted. We installed also a set of heat flux meter, a set of temperatures to control by different way how far, once we were triggering thermal runaway in the central cell by an internal heater that has been provided by the cell provider, which is the coordinator of the project, the French company Saft. And here you have the visual of the tree cluster. You have a side view and a top view.
Sorry to interrupt you. So could you just try to conclude in 1 minute or so?
I will need, I would say, 2-3 minutes, please.
Okay, but then we skip the questions.
Okay,
so go ahead.
So yeah, it's better like that. So here you can see from the graphs showing the measurement of gases that when we were testing the cluster initiating the thermal runaway in the central cell, we have real propagation to the nearby cell. This can be seen from the 3 peaks corresponding to the propagation from the central cell to the 2 nearby cells. What you also observe is that the first thermal runaway is just degassing, because it's essentially CO that we get, and also organic carbonate release, while for the second and the third cell, it's going into flaming combustion, and then we have more CO2, and also it's favoring HF emissions that you can see as well. And this is also, this can also be concluded from the temperature measurements. I will not go into details, and also from the heat release rate measurements, or you can see really the 3 different peaks corresponding to the propagation. Once we went to the module, hopefully, this was not going to propagation from clusters to clusters, and this was the big achievement we got. So we do exactly the same. We initiated the thermal runaway in the central cell of the cluster, and we observed that no propagation was observed on the nearby cluster. So the heat barriers and the heat sinks were perfectly working, at least at the cluster, at the module level. And this was the big achievement that we wanted to get, because this was the core duty. We had to go to a safety approach, which was to develop a fail-safe operational car. We measured also a number of, we did also a number of measurements on the particle side, showing that we are recovering metals from the cathode, the NMC cathode material. We did also some modeling work to confirm the propagation or non-propagation issue, depending on the, we are working on the cluster level, on the module level, and I will not detail this. It's done by CFD models combining the use of Firefoam and FDS codes. And I'm going now to my conclusions. This joint presentation illustrating the type of contribution that can support safe and sustainable use of lithium-ion rechargeable batteries. We show the importance of consolidating efforts in establishing widely accessible incident database. I think it's a key issue that we should be able in some time to have something consistent at the world level, because e-mobility is a world issue. We also show the usefulness of pertinent testing, combining to modeling approach when possible, either to appraise lithium-ion battery intrinsic performances, but also efficiency of multi-layer safety approach. Fast innovation in mobility requires a holistic approach to find best compromise in terms of expected performance increase, market cost compliance, and safety target compliance as well. And eventually, we hope that the audience has appreciated the synergy that we try to bring by this joint communication, intending to capitalize on major output from two originally fully distinct research actions and distinct funding bodies. Thank you very much, and I'm ready to answer questions.
Yeah, thank you.
Time to do that.
No, there is no time for questions.
Okay, sorry for that, but I will answer them at later stage, no problem.
Yeah, and thank both of you for interesting presentations. But unfortunately,
thank you much.
Yeah, but as I said, we don't have time for questions, so we will go directly to our next presentation, the last one before a short break again. So it's Stefan Klee that will talk about fire safety of lithium-ion traction batteries.
Yeah, hello.
Hello, Stefan. I will start.
Okay.
And now you have the
control. I have the control now? Okay. Okay, yeah. Hello, everyone. My name is Stefan Klee. I'd like to talk about the fire safety of lithium-ion traction batteries. And okay, do I have control? Okay, I have. Okay, and the work I'm presenting is done within the research project Superman. It's a German research project. This is funded by the ministry, and it lasted the last 3.5 years. So it's about to end very soon. And what the focus of the project is that we're going, like SUPERSARIN is the acronym for the safety of urban underground structures due to the use of new energy carriers. So we're going inside underground structures, which should be a lot of car parks, for example, or tunnels. And the new energy carriers is what we're defining is, we're looking mostly at lithium-ion batteries, which I'm presenting, and electric vehicles, but that in the project it also included CNG vehicles or other gas vehicles at the same time. Just a few words about the participants of the project. One is the Fogtech Fire Protection. It's a company from Cologne, Germany, and working in the field of fixed firefighting systems. That's the company where I work from. We are accompanied by Stufa, which worked on us with the paper as well, and BAM, it's the third major partner of the project, the Federal Material Testing Agency. We have some associated partners from France, like Ineris and CTU, and from Germany, like the Deutsche Bahn railway station and service, and the firefighters from Munich, as well as the two subcontractors, IFAB and Ineris, which I would mention IFAB most because they were mostly doing the fire testing, which I will be mainly presenting today, and they were part of this whole presentation as well. Just the small background, I think we've heard and seen similar slices in the last 1 or 2 days as well. It's like electric vehicles are, the number is increasing. They're not very high at the moment in most countries, but there is no idea that this trend, which is going up, will stop. And of course, electric vehicles are catching fire like all the other vehicles as well. And so there are some uncertainties about how to deal with these fires. And we're trying to get to a track on how to deal with the fires from like both the side from a facility, like from a car park or like from firefighters. And our approach was that by fire testing, we did a couple of fire tests series. And the first one was mainly to get a major understanding about the burning behavior of lithium-ion batteries as they differ from like the common fuels you find in a vehicle like a gasoline or diesel. So what was important for us was with our fire testing, we were going out to get real scale testing. At least we wanted to get like a real fire load. As when we were looking at the start of the project, there were a lot of fire testings done with lithium-ion batteries, but a lot of them and most of them were on cell level. And we tried to go beyond that and trying to see what happens if an entire module or a battery pack for an electric vehicle catches fire, and how does it propagate? Because if we have to deal with it from the facility side, like car park, so my most common example here, we have to deal with all of that. And we were lucky to get a cooperation with the German manufacturer, and we actually get a couple of batteries and modules. So we're not the one on the pictures. We're testing in the tests I was sure I will be showing. Okay, the ignition of the cell is we started the thermal runaway can start with a single cell, even if it's a pouch cell or it's a cylindrical cell. For example, it starts with one cell. And that was how we tried to initiate the whole process. And we would try to observe the propagation and at a later stage, see how we can stop the propagation to other cells inside a module or battery pack. And for the first fire test series, we were getting for the burning behavior, we have set up this calorimeter. There's a picture on the left. And we designed it to match the purposes of our research project. The battery, the fire load was placed inside of this. We had a door so we could load everything and get everything out after the tests. And we did a lot of measurements. We had temperature measurements starting from the surface of the battery, the gas temperatures inside of the compartment. And of course, there was another battery temperature measurements in the exhaust duct. And we were going for the heat release rate of the batteries. And we tried 3 different measures. One was the oxygen consumption method. So we got the gas measurements from the exhaust duct. We have a weight scale to get the mass loss rate of the battery, and another method more based on like the energy balances, but that was more like our scientific partner going for that. We measured the velocity to get a volume flow out of the compartment and the end of the duct, which you cannot see over here. There was a ventilator and drawn out air out of the compartment. We measured gas concentrations with some single gas measurements, some multi-gas sensor with an FDR technology, and we took some analysis of the fire water to get in the cases we made suppression tests. And for the first quick showing of some results, I get the time-dependent main acid species. We measured, which is from a pouch cell battery, a large pouch the battery. And we've measured, of course, its HF peaks all the time, and they represent the way the way the battery burned. There was like jet fires getting out of the single pouch cells. Sometimes they were larger. It was up to 1.5 meters. If there was probably more cells getting at the same time or nearly at the same time. And this kind of battery reacted for over an hour. And this is a picture you can see is here. With HCN measurements, there is an earlier peak around 20 minutes. And so this is probably more from like there was a plastic cover for the batteries. And so it's not directly from the cells. And in addition to that, we have 10 other toxic species that were measured. And this is the heat release rate from the same fire tests. And again, this is just the time that the battery fire tests last for. Like here, it's 70 minutes, and there were peaks to start it. It shows up with peaks, and yeah. For a second fire test series, we are going for takes everything we've learned about the battery fires and go to how we can detect and fight the fires in a potentially afterwards real case scenario. And we were doing fire tests with an adapted fire test chamber as we installed basically, like you can see on the right-hand side, we had a flat roof as we did not need any forced ventilation anymore. And it was easier to install and more realistic to install firefighting components on a flat roof like the one here. And obviously we did not make any heat release measurements with this setup, as we didn't. We made the weight scale, but we didn't measurements based on the gases anymore. We got two variations of fire tests, as we had little ventilation openings. We could seal them or we could open them to get ventilation air in. So that was depending on the type of firefighting agent, obviously if you were testing gaseous firefighting agent, we had to seal the compartment and so not interfere with firefighting agents. We have a lot of measurements, temperatures, and gas measurements as well, doing the same fire test similar to the one before. Our fire test scenario for the suppression agents to get like a comparable scenario for the agents, where we were defining a reference battery fire load, which is can be seen on the top image, and there were basically two modules with cylindrical cells. We have made fire tests with them before under the first series. In total, we had 5 kilowatt hours electrical capacity, and the two models are separated, but we placed them near to each other, but they were uncovered, which is an important thing to know, that when we activated the firefighting systems, they get an uncovered fire load. The ignition for ignition, which choose to overcharge the cells, like with so that we started with a single cell. You can see on during the heat up process on the right-hand side. These are the firefighting agents we have tested. We went for water-based and sprinkler, obviously, low pressure mist, high pressure water mist, and we've made high pressure water mist also with an F500 additive, and we tested some firefighting foam. And then with the sealed compartments, we were for aerosol, Norvac, nitrogen, and carbon dioxides. We had a criterion to activate the firefighting systems, which was the same in all fire tests. And then when we reached a mean temperature in the fire test chamber of larger 50 degrees, which is more or less in the upper layer, we had, I think, 10 thermocouples, and then we took the mean value, and then after reaching 50 Celsius, we activated it. One slide here for the time it took to ignition. We have made a total of 13 fire tests with this setup, and on the right-hand side, the bars are the time it took into the failure of the first cell, like when the first cell bursted due to the overcharging. And during all tests, it was just this one cell failing and starting then the propagation to the next cells and the other modules as well. So we have between 45 and 75 seconds after the start of the overcharging, the first cell failed. So we got a kind of reproducible ignition method, which is important for our setup. Here's some reference. This is a reference fire load in a free burn process. And one was the one with the mechanical ventilation. The green one was was performed with the first kilometer I've showed. And what is one thing was important to know for the comparison with the firefighting agents is that the thermal runaway propagates to both modules in all fire tests we have done if we do not interfere in any way. So there was a thing, if you do not put any firefighting activity, the whole battery modules will get burned. So we have something to go if they do not get burned, that is the effect of the firefighting agents. And what we can see here from like the speed of propagation, that is depending on oxygen as a lot of other fires as well. And just a quick summary for the results of our detection and firefighting series. All the firefighting agents, or most of them that we put into the scenario, did protect the second module and could stop the propagation at that point. There were the general trends that the surface temperatures of the batteries are higher, and that temperatures last longer, higher temperatures last longer with gas-based agents. And another observation was that the water from our sprays, and we used a lot of water-based agents, did not cause electrical problems as far as we could see, and by failing inside the battery or the second module. So I coming to some conclusions from the research project. One is that the lithium-ion traction batteries, they release significantly more energy than their maximum electric stored capacity if they burn, as this comes to the the electrolytes or other components burn after failing the cell. And that the burning rate, heat release rates depends on the design of the cell and especially on the cell type, as we have like the pouch cells I've put in one fire test, and the cylindrical cells, there are the different fire behavior, especially in kind of how quickly they propagate the thermal runaway to other cells. And another finding is that although the gas released by the lithium battery cells that we have tested are combustible in all the cases, they did not ignite in all the time. It's like sometimes there was a cell gas off for a cell for the first time, and it did not ignite. And there is a mix of toxic and reactive gases that is emitted if a cell bursted. HF is the most prominent one, but it's not by far not the only one which is dangerous out there. And of course, like the exothermal reaction that gets inside the cells and that keeps firing up and propagating to neighbor cells, even if there are no cells visible at the moment when observing. The second part of the conclusions is that we were able to stop that the thermal runaway, the propagation can be stopped. We had with several more proven firefighting agents that the propagation to a second really close by module could be stopped. And we had fire tests even where we could stop the propagation within a certain module, for example, with water mist, possible. And as the exothermal reaction keeps firing up, the cooling is a recommended strategy to stop the propagation. What we also acknowledge that the status of the lithium-ion battery after the fire test cannot be accessed just by a visual criteria. If you look at it and it doesn't, or it seems okay, then it doesn't mean it's not able to ignite at some point, as a reignition or a late ignition of damaged modules were always possible. We observed it after several days of the fire test. And for the conclusion for what firefighting agent to take, I think it will come down to most agents have their strengths and weaknesses, and so one have to decide for the case which one would you like to use. So now I'm nearing the end of my talk. This is just the outline of what we're doing with the Silverwind project. We're about to publish some guidelines as we're the end of our project, and we will go on trying to with follow-up projects to go with this NEC direction. And yeah, thank you very much. Any questions?
Thank you very much, Stephen. A very good presentation. So we have a question here. So why did you consider 50 degrees Celsius for activation of fire suppression?
It's in a way we had to put one number to start it. Most important thing was to get the same criteria for all the fire tests. And it was like we had free burning tests of the same fire load. And then after that, we looked at the data and tried to evaluate what was a good starting point. The most important thing is we didn't want to start with the first burst of the cell. Like if there was the first cell, so we tried to get the criteria where we were sure that the 50 degrees only were reached after multiple other cells went under thermal runaway as well. And so we really there was an active reaction inside the battery. And yeah, that was, so it's like the 50, it could be 55, but that's around the reasons how did we get it.
Thank you. So, and another question. So what equipment did you use for measurement of the HF? And did you see any difference in the data when fire suppression was considered?
We used an FTIR sensor to detect the HF, and so I think that is in a way always affected if you get to a water-based suppression agent, that there's more water vapor, and so if you get to measure volume percentages or ppms, there is always an effect. And so I'm not too sure what I cannot really state a real thing between the HF with suppressed and unsuppressed. So it's sorry, I can't go for the more clear answer here.
Yeah, and then another one. So I thought you mentioned analysis of the contamination of firewater at the start of your presentation. Did you gather any information related to this?
Yeah, we have detected heavy metals in the firewater for all the fire tests we've mentioned. We haven't different amounts, but the firewater afterwards is we're finally evaluating this, but there's contamination and pollution from heavy metals in it, and so there might be a consideration to deal with if you attack with a fire with water, which is the most common firefighting agent, especially for firefighters, like not the fixed, but in that sector as well. So.
Yeah, and maybe a last question then. So almost all modern battery packs are liquid cooled, to my knowledge. It says thermal runaway tends to spread slower or even stops in these packs. Are there any tests done with modern liquid cooled packs? Is the question.
No, we did not do that. It was hard to get. We took the cells and the battery packs you could get, and so we didn't have this kind of cells. But that will influence the propagation, as the cell type, even from cylindrical cells and pouch cells, is really different in propagation, and so that will affect it for sure.
Okay, thank you very much, Stephen.
Yes, thank you for having me.
And yeah, the clock is 20 past 11, and as you see, we will have a short 10-minute break until 1/2 past, and then we have 2 more presentations to go. So see you in 10 minutes.
Okay, so it's past. So welcome back to this final session of 5/2020. And I would like first, before we go into the presentations, ask everybody to, when you put the question in the Q&A, please also mention which speaker you're directing it to, because we have had a few questions where it was difficult to determine which speaker it was for. So by that, I would like to introduce the next presentation, Emergency Responses in Smoke from Lithium-ion Batteries. And it's Niels van Veen who will do this presentation. So I should give the remote to him. So Niels, are you with us? So Niels, we cannot hear you. Okay, so you are.
Petra, can you hear me now?
Yes, I can, but something happened here now. So, okay, so I need to share again. Sorry about this. Sorry about this. Katten hittar man bildspelet. Jag kommer inte åt den. Där nere. Okay, so now, so I give the remote again. So here. And then please click on, oh, sorry, I should go forward here before I do this. Okay, and
Yes.
now I will give the remote again here. So sorry about this. Okay. So now you should be able to control. Just click on it.
Okay. Okay. Well, thank you, thank you, Petra. Well, hello everyone. Thank you for the opportunity to present here something. My name is Niels van Veen. I've prepared this presentation together with Arjen Koppen of the National Poisons Information Center. And I'm working at the National Institute for Public Health and the Environment. And within this institute, we have an emergency service for environmental accidents. And this emergency service was involved in a large fire of a lithium-ion battery storage about 2 years ago. And we realized that after this fire that we needed to gain more knowledge on this subject. And in collaboration with this fire brigade, we have carried out several fire experiments. And I would like to show you a selection of these experiments. And let's see if my control works. No. Yeah. With a small delay. Okay, and the experiments that we carried out were all focused on health issues for firefighters that have to intervene in smoke. This is smoke from a parking garage where an electrical car is burning. And we wanted to check the protective value of the firewood that we consider as the most vulnerable part of the entire fire suit. We wanted to see how HF concentrations develop over time, because what you see in many pictures is that HF concentrations as a very reactive gas can decrease rapidly.
Sorry.
Yes?
You're breaking up a bit sometimes, so maybe you should turn off your video.
Okay. You have to close the presentation to. I can see the video screen right now.
Well, okay, so just continue.
So you have to close the presentation. Okay, well, I'll continue. So we have focused on the risks of HF in particular for firefighters. We have basically done this by collecting HF containing smoke by burning lithium-ion batteries. And we collected the smoke. Well, the console is not working.
Click on the screen. I think you're.
Yeah, it doesn't work.
Okay, it says, but okay, so I will do it then.
Yeah. Okay, so you can click now. So we collected the smoke and we measured in the smoke filled bag over time. We measured it with two type of detection devices or equipment. One is FTR analyzers and the other is gas washing bottles. And we place samples inside the bag with one part HF absorbing filters, the whitish thing that you can see here, and the other one was a PVC pipe covered by a fire hood. At the end of the experiment, we next slide, please, or next.
Well, you are in control now, so you can click on it.
It doesn't work. It worked fine during the test, but it doesn't work anymore. Okay, we made surface swabs of the contamination after the experiments, and we took these swabs, this surface contamination on both bottom and ceiling of the bag to see the difference of those two. Next slide, please. Okay. Well, you have to click a few times now. Yeah, well, what you can see, we performed 4 tests in 3 different bags. And if you can click the next again, we used for experiment B and C exactly the same battery with the same state of charge. So you can go to the next 2 steps again. We exposed 2 types of filters. We exposed unprotected HF containing filters, and we exposed protected filters. Can you click again and another time? And another time. Yeah. So these filters were protected by or dry pieces of firewood or slightly moistened. And we've chosen to moisten the firewood because during a fire, firemen can sweat when it's very warm, and there can also be water vapors in fire present, and this could lead to a moistened firewood. From isolation point of view, thermic isolation, it's not ideal to moisten a firewood indeed. You can do the next slide. Okay, so what you see here, these are the results of the PVC pipes and the HF absorbing filters. And what happens in smoke from lithium-ion batteries, there is a lot of HF being released, but also a fluoride-containing salts, as what we can see out of our experiments. And HF can be absorbed by smoke particles or can be absorbed by water mist droplets, and this is forming aerosol. Well, if these aerosol from HF or fluorine-containing salts would go through the barrier of the firewood, then we would be able to find this on the PVC pipe back. It would condense there if it would happen at high rates. And yeah, you can see the green numbers here. It's below the detection limit for quite a large surface. So in this experiment, we didn't notice any we didn't notice any breakthrough of the firewood for particles. If you look on the left, filters, then you can see that there's a very high, in comparison, a very high breakthrough rate at this point. Can you click the next slide, Petra? And the next, click a few times. So what we can see is that anhydrous HF, so this is just the HF molecule, this is not retained by the firewood. Well, click again, please. Now, if we look further to the results of the HF filters only, then we can see here different results of the test. Well, you can see the first test, we had very low concentrations of HF. And the second and the third test were quite similar. And what we can see is that a wet firewood has approximately, well, it's below the detection limit, so we couldn't detect it, but it's at least 50% of the amount of hydrogen fluoride that went through the firewood in comparison to the dry firewood. And in comparison to the unprotected filter, we can see that this is again twice as much in comparison to the dry firewood. So a normal firewood protects also during long interventions. This is a measurement time of about 60 minutes. That it helps to protect against HF, but it doesn't fully protect. Well, can you click a few times? Yeah. Okay, again. So yeah, what we see here is multiple exposure. We've also exposed a few samples multiple times to all the experiments, and what you can see here is that the difference between the dry and the unprotected is different. If you can click again, Petra, then this is very interesting, because what we did at the end of every experiment, we removed the samples from the bag, and the samples without protection were directly exposed to clean air, and the exposure of HF stopped. The filters that were still present like this, with if the firewood around the HF filter was saturated with HF, and the exposure continued even after when the sample was removed from the smoke. Can you click again, Petra? So what we can see is that the exposure continues after removal from smoke. Well, you can click again a few times now. Yeah, okay, stop here. Oh, can you go back? Yeah, so what we see is that the Nomex firewood, it retains at low concentrations at least fluoride containing aerosol. It reduces exposure but doesn't fully protect against anhydrous HF. The exposure of anhydrous HF continues after the response, as long as the firewood is not removed from the firefighter. So it's important that this is taken in account after an intervention. And what we have also clearly seen is that moistened firewoods reduce gas diffusion compared to dry. Well, can you click to the next slide again? And you can click and click and click another time, and that's it. Okay. So what we go now to the other subject. This is the decrease of HF. What we've seen in experiments that if you see HF, that the HF concentrations decrease very rapidly. And what we wanted to prove is that if you catch a smoke from a lithium-ion battery fire, that the HF is decreasing much faster than inert gases. Well, this is the carbon dioxide, and you can see that HF is disappearing very fast. And this is happening due to condensation on the surfaces of the bag, but also due to absorption of smoke particles. And the positive thing is that the HF concentrations will decrease in air, and the negative consequence is that the pollution rates will increase higher, because everything that disappears from the smoke will be present as pollution on surfaces. And it's very important to take this in account when you calculate with concentrations, because if you calculate a concentration of for let's say 20 ppm, then you have to take in account that after a few minutes, even with zero ventilation, that the concentration of HF will decrease rapidly. Normal rooms also have very strong ventilation rates. So in a normal living room situation, after 20 minutes, you won't be able to detect any HF anymore after a fire. Okay, can you click the next slide again, Petra? Yeah, click again until you see the red barrier. Okay. Well, if you look at the surface contamination, we can see that well, what I just told, that decrease of HF leads to important pollution of surfaces, and there's a very large variety in the consistency of the pollution between the different batteries. So what we can see is that the iron phosphate batteries, they have much lower pollution in comparison to the NMC batteries. And we think we reported all the fluorine ions. This is measured by ion chromatography, and what we can see here is that we basically report the fluoride ions, and we have chosen for the most worst case scenario, and that's the reason why we report in HF. But we think that the major part is not HF, it's fluorine containing salts that you can see here. You can also see that there's a very high percentage of lithium present, mainly as lithium oxide or lithium hydroxide. Well, you can click again to the next slide. The conclusions, next slide, yeah. Click again and again. Yes, and one click, okay, yeah. Could you go back? Yeah, so what we can see is that the concentrations of HF in smoke decrease over time, and the fastest decrease is in the first 20 minutes. It's possible that air humidity, smoke density, and consistency might impact this decrease time. And as a result, we have lower HF concentrations in smoke, as you would expect normally, and there's a considerable pollution of exposed surfaces. Well, this is already pretty well known. Can you go to the next slide, Petra? Yeah, and click again. And again. And again. And again. And again. Okay, so if we look at the toxicology of HF, what we can see that there are different health consequences. And if we look at a firefighter that's wearing breathing apparatus, the only, well, and a mask, of course, the only exposure way is the skin. And if you look at the health consequences, then the most important is local effects and systemic health effects. And systemic health effects depend on the absorbed dose of HF. And it starts with mild symptoms, and at severe symptoms, they can become life-threatening. And the first mild effects for an adult of about 70 kilo start at the dose of a bit more than 200 milligram HF. Now, if we look at the local effects for a firefighter, as I said, skin damage is the possible local effect. And this will start with pain and further irritation of the skin. And at higher dose, it will go over to chemical burns. Well, we have performed a literature study, and the only information we found about exposure to anhydrous HF was an exposure of 2 volunteers that were 1 minute exposed, unprotected, to a concentration of 100 milligram per cubic meter. And they reported starting of smarting at the skin. Can you do the next slide? And click again. And again, yeah. Oh, and back. Okay, so what we have done, we have extrapolated the detected amounts of the experiments. We have taken the area under the curve of all the detected HF, and we have recalculated, extrapolated this to a 20 minutes exposure at 100 milligram HF per cubic meter. And if we relate this to a skin surface of 500 square centimeters, which is approximately the neck, then a firefighter would receive a dose of 4 milligram HF. Well, and this is the point where local effects can start, and the conclusion is that local effects will start long before systemic health effects. Can you go to the next slide? And you can continue until you see the lithium hydroxide at the bottom. Yeah, thank you. Okay, so local effects on the skin, they depend on the concentration. At first, the higher concentration, the higher the consequences. But more important is the exposure time, and this is clearly visible in this rabbit tests that have been carried out. And you can see that the 5 minutes exposure to a solution, so this is not gas, but a solution of 0.1% HF leads to visible skin damage. And the rabbit exposed only 1 minute to a 200 times higher concentration had no visible skin damage. So the exposure time seems to be more important than the concentration for liquids. And this is also logic because the penetration speed of HF is, well, about 1 millimeter for every 10 centimeter, for every 1 millimeter for every 10 minutes. And it's clear that the deeper HF gets into the skin, the more severe the effects will be. And we can see that an increased exposure leads to increased skin damage. So after a response with elevated HF exposure, it's very important to rapidly remove the fire hood and start with adequate contamination. And this is not driving back to the fire brigade and taking a shower over there. But if you have worked in really high concentrations HF and there's a skin smarting, then you should start rinsing water immediately. And after consultation or with a medicine, you could consider to apply calcium gluconate gel, and this should also be quickly available, of course. Well, some lithium-ion batteries lead to emissions of very high concentrations, lithium oxide or lithium hydroxide, and this is basically a positive impact of the risk of HF. Can you go to the next slide? So if we look at HF, and you see this as an acid, so HF dissolved in a solution, then HF is a weak acid, which means that a part is dissociated into hydrogen and fluoride ions, and a part is present as HF. The proportion of these two is also depending on the pH of the liquid. If we would add hydrochloric acid in concentration, concentrated hydrochloric acid, then the pH would decrease and there will be a larger part of HF present in the solution. If we add hydroxide by lithium hydroxide, then a larger proportion will be present as hydrogen ions and fluoride ions. And this is mainly a positive thing. Well, could you click 3 times, Petra? So what happens if you see HF, when it touches the skin surface has a pH of about 5, it's a bit acid, and it easily penetrates the skin. And then at deeper tissue, the pH increases. The blood has a pH of about 7.4. And at these pH levels, HF is dissociating rapidly into hydrogen ion and fluoride ions. And the H+ ion is not a big risk of hydrofluoric acid. Can you click again?
Yeah, and I think we should try and wrap it up also. So because the time is running.
Yeah. Can I continue still?
Yeah. Yeah, but try to do the conclusions.
I'll finish this. So the biggest problem is that the salts that are formed inside the body and also reactions with enzymes. And could you click again? So if you increase the pH, can you click again? So by increasing the pH, you have more fluorine ions, and fluorine ions are not able to penetrate the skin. And this is because of the shifting of the equilibrium to the right. So this is basically a very positive point in that you have to take in account with fire response. Well, Peter, I don't know what you want. If you want to continue.
Well, I think
this is the last slide. You can click again.
So
yeah, you can stop clicking now. So okay.
So I think we should move on to.
Okay.
Yeah.
Then we stop. Okay.
So maybe you could just say a bit on the detection side here.
Okay. Okay. Well, we have tested different detection devices, and what we've seen is that fluoride testing paper is basically the best thing that you can use during fire intervention, because it's easy to use, it cannot break, and it does work for every fluoride ion. So it does also react on toothpaste, as you can see here. There's sodium fluoride in toothpaste. But it changes color rapidly, and it doesn't tell you if there are dangerous concentrations present, but it tells you if fluoride concentrations in the smoke are present. At higher concentrations, you can see a very fast reaction, and the paper changes color very rapidly. At lower concentrations, you can first see color change at the edge of the paper. Well, you should normally drop them into a hydrochloric acid solution with a pH of 1 or even lower. But we've seen it also with water, it works fine. What makes it easy applicable for firefighters. In dry situation, there's a more eagle color change, and it makes it harder to read. So it's also good to use a reference and to read these papers out. Well, the conclusions are visible here. Skin damage is the first revealing risk.
Sorry, Nils. So I think we will have time for one short question. So thank you very much, and sorry for these technical problems. So we have a question here. Was the fire hood with or without the membrane between the hood layers?
It was a fire hood. There was the membrane was inside, but this was not a specialized particle barrier. That's not a nanoflex particle barrier. It was a normal Nomex fire hood, and we only used the double layered part. And I think that the nanoflex barrier will protect even better than this one.
Okay, and so a very short one also. How wet was it? Was it
well, we added we immersed the fire hood, and then we squeezed all the water out. So it was just only 8 grams water per 100 square centimeter, which is not a lot. It was just really slightly moistened.
Okay, thank you very much. And there are more questions in the Q&A, so please feel free to answer them there. Thank you very much. So now it's time for the final presentation of this conference, and it's a face you will recognize. It's Ola Willstrand, who will talk about toxic gases from electric vehicle fires. So I start the presentation and give a remote. So please go ahead, Ola.
Yeah, thank you. So I thought maybe the virtual 5 background would work, but it seems not to. But anyway, so I'm sitting in my office now. So when I'm not organizing the 5 conference, I'm a project manager at RISE, and the project I will talk about today is an ongoing project named ETOX, and it's soon finished. It will finish this year, but right now actually my colleagues is analyzing the simulation results that have just been finished, so I will not be able to present that much results from the simulations, but some. But I haven't seen all the results as well. But we also have done a literature study and maybe most interesting, some full-scale vehicle tests and some battery tests. And this is financed by the Swedish Energy Agency, and we have some project partners, insurance companies, rescue services, the Civil Contingency Agency, and the scrapyard. So with regard to the literature study, we have compiled previous tests, both on electrical vehicles, but also on batteries, standalone batteries, with regard to gas and heat measurements. And what we did was a simple analysis where we just compared the maximum total quantities that have been measured for different substances in any of these studies, and then compare them to listed health exposure limits. And we used the IDLH, immediately dangerous to life and health, and acute exposure guideline levels, as well as Swedish requirements from the Work Environment Authority. And what we saw was that there is not one specific substance that it's easily to say that this is the dangerous one. We could see at least these ones had quite high amounts in at least one of the studies, but the variation was also quite large. So if you go to a specific study, you would also have in some cases hydrogen cyanide and nitrogen oxides, as well as other metals and organic compounds, and not all organic compounds especially have listed health exposure limits as well. And we don't take into account combined effects and so on. But the conclusion here is that, I mean, if you inhale smoke from a vehicle or battery storage or anything, there is probably many different toxic gases here, and it's hard to say that, for example, HF is the most dangerous one when inhaled with the smoke. So I will come back to some more results from the literature study when I present the results from the tests. But so this is the 3 vehicles that we burnt in the project. In test 1 and 2 here is a van of the same model from the same manufacturer, just different powertrains, different model years. But yeah, we got the vehicles from the insurance companies and couldn't decide exactly what vehicles we got, but I think still a good comparison. And then a third vehicle, a small family car, full electric, battery electric vehicle as well, from a different manufacturers. As I mentioned, we also did some battery tests. So as you see in this picture here, from a battery pack fire, you see it's missing 3 modules here, and these were actually then used for module and cell level tests. So we had exactly the same type of battery cells in different scale of fire, and the purpose was just to see the scalability of measured quantities. So we start to look at the heat release. So at the bottom here, you see the heat release rate curves from the 3 vehicles. So we had started with a fire underneath the vehicle at 5 minutes, according to this graph. So after another 5 minutes, the diesel tank burst for the diesel car and the diesel van, and the fire development was then much faster compared to the electric vehicles. So the purpose here was to try to get the battery involved at the same time as you have the peak heat release rate from the rest of the car, and I think we succeed with that. So that's why you got quite a high peak for the same model van here at 7 megawatts for the electric one. And this was also pouch cells, so you got the propagation very fast, so all the battery gases were ventilated in about 10 minutes, and also contributed to this high peak. For the third test, there was prismatic cells, and this you could see one cell after another popping and ventilating, and the ventilating continued for at least 20 minutes. So that's why you don't see any significant change of the heat release rate curve. And also to the right here, you see from the literature, if compared with other tests from the literature, that yeah, it's similar to what have been measured before. There's no big difference between conventional cars, ICE vehicle, internal combustion engine vehicles, the red dots here, and the electric ones, plug-in and full electric. There is a larger variance for the conventional ones, mainly due to the liquid fuel. So if you have a empty tank or full tank, and also of course the size of the vehicle. But for the batteries, you have all the chemical energy there, independent on the state of charge. And for the total heat release, it looks very similar, the variation here. And if we look a little bit more on the total heat release, we can also see from battery tests. So this graph only shows battery tests, free burning batteries, no vehicles. And the blue ones here is from our battery tests, and the other ones is from the literature. And if you compare total heat release to nominal electrical energy, you can see quite a good linear trend here. And then if we see for the vehicles, you see in the red circle here, if we use this linear trend for this 40 kilowatt hour battery we had in test 2, then that would mean that you have 1.9 gigajoule of heat energy in a fire compared to the 44 liter of diesel, which is less. So test 1 and 2 here is the same type of car, but if we look at what was measured from the vehicles, you see the opposite, and this is explained by that the diesel ran out, burns effectively, while the batteries is integrated into the vehicle and the oxygen supply is limited. So what I'm trying to say here is that this linear trend could be a good way to conservatively estimate the maximum energy that you can get. But in a real case, if you have limited oxygen supply, you would get less. And then, of course, in test 3, you have higher because of more combustible material in the passenger compartment compared to the vans. And then if we move to the gas release instead, which was the main focus here, we could start looking at the from the literature. It's basically tests performed in France by Ineris, and also one conventional vehicle added from a test at RISE for almost 20 years ago. And what you see is, yeah, it's quite similar, independent on the powertrain, except for the hydrogen fluoride, where you can see a distinct difference. And then if we add measurements from our new test now, we could see that they are quite similar, a little bit lower, could be due to that we have vans and a quite small family car with less combustible material. There was less total amount of HF, but the difference here between the conventional car and the electric ones is almost the same. We could also see a difference in the hydrogen chloride, but that could also depend on the different plastics for the fuel tank and the drive lines. Actually, in the previous test in France, it was the opposite. So then there was more hydrogen chloride for the conventional cars. So the significant difference here is for the HF. And if we look a little bit more on the HF then, and by the way, very interesting presentation, the previous one that also talked a lot about hydrogen fluoride. So the graph to the left is from our battery tests at cell level and module level and battery pack level. And you could see a good linear trend here, 30 milligram per watt hour. And then if you look to the right, you see the HF graphs measured by FTIR from the vehicle test. And you see an initial peak here, probably from the air conditioning system, the AC gas that contains fluoride, and the second one from the battery, because the second peak here is also confirmed by visually that you see that the battery ventilates at this time. We didn't get any peak at all for the diesel van, and that's a bit surprising because we checked the AC system, the pressure of the AC system before tests, and also it should be a fluoride-containing AC gas. But anyway, to estimate the contribution from the battery here, we just integrated the second peak in these graphs, and that's what you see on the next slide here, which is the square dark blue dots estimated from the batteries, and the light ones is totally from the vehicles. The blue ones is from the in-air tests, and the estimated contribution from the battery here is only the difference between the electric vehicles tested and the conventional ones. So these 4 vehicle tests is basically the only ones that have measured toxic gases in detail from vehicles, electric vehicles. And then you can see some interesting trend lines. So the black one here is just the one that you saw before from our battery, 30 milligram per watt hour. The green and red lines is from previous battery cell tests at RISE, ranging from 12 milligram per watt hour up to 200 milligram per watt hour. And the interesting thing here is that it's the red one that has been used or discussed as a worst case scenario by a rescue service, for example, and yeah, it's always good to estimate worst case scenarios, but this would then mean for a 40 kilowatt hour battery, for example, it would mean 8 kilogram of HF, and for a Tesla with 100 kilowatt hours, it would mean 20 kilogram. But from the 4 vehicle tests we have less than 1 kilo from the batteries, and yeah, of course, it's only 4 tests, so it's hard to draw conclusions, but it could also be explained because there's other tests showing that if you compare, for example, burning electrolyte as a pool fire compared to when the same amount of electrolyte is within a cell, you get much less HF out from the cell due to wall losses, because the HF easily reacts with any solid objects and particles and so on. And if you integrate that battery into a vehicle, you would get even less HF out in the smoke. So that's could be a reason to measure less from a vehicle compared to a battery cell. I should also mention that on the soot particles, there is a large difference with the metal content, and as you see in this graph here, and it's metals from the batteries. It's nickel, cobalt, manganese, lithium, aluminium, and yeah, copper as well. So there's quite limited research done on both on the health effects and the environmental effects of these metals. We could see that the total amounts in our tests would not cause a major health effect compared to the other toxic gases, but the environmental effects could be interesting to study further, and that's also our plans for future projects. And you could also see for the fluoride content here on the soot particles that you have also much more for the electrical cars, and especially in test 2 here, you have quite high 190 grams, and as you saw on the on the previous one, that you have a quite low value for the FTIR measurement. So I mean the HF also gets stuck on the soot particles. So, and then as I mentioned, we also do some simulations, and I should just mention quite briefly about those. So we have tried to find a worst case scenario. So we chose an underground parking garage, basically where you fulfill requirements for natural ventilation with only the garage door and also some small just leakage through staircases and so on. So no mechanical ventilation, but still as large as possible, such that you have actually have to go inside when you fight the fires, basically. So you have still a garage with 65 parking lots here. So and then we had different fire locations close to the door and as far away as possible, and different ventilation scenarios with the door open entire duration, and if the door is opened by the rescue service when they arrive after 20 or 35 minutes. And it's the small family car that have been used as the fire here. And and we also had some other ventilation scenarios with cross flow, as well as one scenario where the fire spread to a second car. And I should I should just say that we're looking on the combined effects here as well. So this is the fractional effective dose based on carbon monoxide and carbon dioxide and hydrogen cyanide, and then we also look at the fractional effective concentration based on all the irritating gases, and the graph you see here is only for, it's not all the simulations, but just an example, and the conclusion is because those fed and FEC values, usually you say 0.3 as a critical one for evacuation, for example, and that occur faster for the concentration compared to the dose, and also before battery gets involved in the fire. And then and then the HF. So you have maximum concentrations of about 200 ppm at head height, 1.8 meter above floor level. And this is really conservative values, since, as also was discussed in the previous presentation, that the concentration of HF will decay quite fast in an enclosure. So so if you fill up a parking garage, or if you have a lot of soul parkers and so on, the HF concentration will decay in short, like 10 to 20 minutes. So you will probably not reach those, because that was not taken into account in the simulations. And and the last one for the simulation here is just the effect of the height above floor level, and when you open up the door. So this is the two cases when you open the door at 20 minutes and after 35 minutes, and you can see for low levels it makes a dramatic difference with the concentrations, but at about 1.5 meter and above, it doesn't make a huge difference, and this is quite close also to the door. So some conclusions from this then. So HF and also some specific metals represent the largest difference between electric vehicles and conventional vehicles. As I said, when inhaled, there are several acute toxic acids released regardless of the type of vehicle burning. And then for the rescue service, hydrogen fluoride is of certain interest due to that it can be absorbed through the skin, but this was very good investigated in previous study or the previous presentation here by Wien. And also I would say for this really worst case scenario with the parking garage, still show relatively low maximum concentration. So I know in Sweden, turnout gear materials have been tested with concentrations, I think it was up to almost 2000 ppm. So and still showed quite good protection capacity. And then and then also peak heat release rate and total heat release are affected by the fire scenario and vehicle model, but not significantly on the powertrain. So I can show the video as well. I think there is 1 minute left, or oh, okay, it was not. Maybe I've linked the wrong the wrong presentation. Then we skip the video.
Okay, thank you very much, Ola. And so we have time for a few questions here. And one has already been covered here in the presentation, I believe, about the AC system. But we have another question here about exposure dangers for investigators compared to that for the fire service. Is this something you have looked into? I mean, when you
sorry. Yeah, we haven't looked at that specifically because, I mean, for the investigator is more on the surfaces, how contaminated the surfaces are. I mean, the HF, as I mentioned, for example, will decay fast, and also other gases will decay. I mean, they will not experience this when you are in the smoke in that way, but for the surfaces, it's still a health threat, I would say. Yeah.
Yes, and so concerning the simulations, what do you think will be the main benefit and use of these simulations once they are finished?
Yeah, I mean, I think for the rescue service, I think it's good to have, and also for a worst case scenario, what actual concentrations of different gases would you experience, and then there could be other studies looking into, okay, when you have these concentrations, how long could you be in there, and what are the health effects and so on. But I think it's very important to know what will you face in such a scenario.
Okay, thank you very much. So I think it's time for us to conclude here. And so I will start by thanking all the presenters here. And I mean, it is a tricky time, this. I mean, we had planned to have a live event, and then we postponed it, and then we in the end decided to go for this solution. And we are not experts in arranging online conferences, so this has been a learning by doing experience. So I'm well, I would like to apologize for the mishaps that has happened here during the conference. When it comes to, well, giving remote and all kinds of things that happens. And so I also would like to remind you about taking a look at the Menti, and perhaps we can have a look at the results we have seen so far. So if I should stop sharing here. Oh, okay, you did it. So the first question we had here was, what country are you in right now? And we still have the answers coming in. So it seems that Germany is the largest representatives right now. And then if we move on, so in case there was no pandemic, would you have attended the live 5 2020 in Amsterdam? Some of you would have, some of you would not. So we can take maybe a look at the next question here. And so how many times have you participated in 5? So it's a lot of people who are here for the first time. And then we have some people coming back from year to year. Okay, so thank you. So we can, and if there had been a fee for the online event, would you have attended anyways? Well, some of you would have, and some of you would not. And we can move forward to the next one. And so this is what you would have been willing to pay. And I'm not sure, I think we have a few more slides here. Yeah, that's what areas you're most interested in. And maybe if there is one more, yeah, about the problems and solutions. So it's pretty much even out here. And maybe there is one more. No, there isn't. Okay. So that's all the questions. So I ask you to really take a look at these and answer the questions. This is very useful information for us to have. I mean, we definitely would hope to have a live event or in real life event next time, because with this behind the computer screen, you miss out a lot of interesting discussions and interaction with the presenters during breaks, and having the benefiting of being able to go and visit the exhibition areas and so on. So we are really, well, fingers crossed for a corona-free 2021, and also 2022 when the next 5 will be. As mentioned previously, we will make presentations available, and there will also be a recording of the actual conference, and this we hope will be available of it before Christmas. But stay tuned in the 5 website to see if it becomes available. We will also post on LinkedIn. There will also be a questionnaire sent out asking what went good, what was good and what was not so good, and so on. So by that, I really would like to say thank you once again to all the presenters who has really been very cooperative and well, across the waters, getting up very early in the morning to give the presentations, and also really trying hard to make this work with the presentations. And to all attendees for all the interesting questions you have put in here, and to listen in to this conference. So, well, you have seen mainly Ola and me here. There is, of course, a team behind us as well, and we should have been 3 here on stage, but due to the corona situation, Roland had to stay at home because he had a cold. So therefore, it's been a bit, well, maybe boring just seeing Ola and me all the time. So, and then we have other people helping up here internally at RISE, Joel Blom, and above all, Kaisa Kaukaranta, who is really managing all the, well, the Zoom things here. And also Jenny helping up, Ms. Solberg helping out with the web page. There is probably maybe someone I've forgotten, but well, thank you to all of you making this happen. And we will try to not close the conference as abrupt as we did yesterday, in case there are more questions in the Q&A. But it will be no more talks here from the stage, so to say. So thank you all, and Merry Christmas and a corona-free 2021. Bye-bye.
Thank you very much, Petra.
Thank you, Guy.
Thank you. Bye-bye.
Thank you, Petra. Bye-bye.
Thank you. Bye-bye.
Thank you, Petra. Bye-bye.
Thank you, Petra. Bye.
Bye-bye.
Bye.